So, hi again. Welcome back to our channel one more time. So, as we said, we are continuing with the example execution example section that we were talking about. Now we are going to consider examples on the Lebesgue dominated convergence theorem. Lebesgue dominated convergence theorem. We're gonna consider examples on the Lebesgue dominated convergence theorem. First of all, let us see the statement of the theorem, and then we will see how we will use it in the example that we come to later. So the theorem states that assume we are given a sequence Fn of measurable functions on a measure set X, and we are also given a function F that is also measurable on the measure set X. But we also assume that the sequence that we have, Fn converges to F pointwise and almost everywhere in X. That means that for almost every X, the limit as n goes to plus infinity of n of x, Fn of X is equal to f of X for all for almost all X in capital X. It means that if we consider the subset of capital S, where this is not true, we get a set of measure 0. That is what it means, what we mean by the point y is almost everywhere in capital X. So assume also that we have a function J, a function G, that is positive, first of all, and that is measurable, and such that for any n, we have the absolute value of our Fn is less than G, and the integral of G is finite. This condition is what gives the name, is the condition that gives the name to the dominated. You see that we have a function that dominates the absolute value of the sequence that we have, and this function is integrable. If all these conditions are satisfied, what we're gonna get? We're gonna get that the limit of the integral of Fn is equal to the integral of f. Equivalently, this means that you can interchange limit and integral. So if you want to compute the limit of the integral, you only need to complete the integral of the limit. This is also very important, as the previous theorem we talked about the Beppo-Levi theorem, but this is more beautiful, more relaxed than the Beppo, because Beppo-Levi needs your functions to be positive and increasing, but here you don't have positiveness, you don't also have increasingness. You only need the function to be, the sequence to be dominated by an integrable function. So we can have a function f that we wanted to integrate, but it was complicated. Then we break it into small pieces of simple function that converges piecewise, pointwise, almost everywhere to that function. And we make sure that the pieces that we have Fn are dominated by an integrable function. For example, if they are bounded on a bounded also set, right? If they are bounded on a bounded set, we know that we can always dominate those functions by a constant, and then therefore we can interchange the limit. That means that when we wanted to compute the integral of f, that was difficult. Now we have a formula for approximating this integral by only taking the limit of the integral of fn, but here we are sure that we can simply integrate those functions and get a very nice answer. So let us see how we can use this theorem in some examples. The first example we're going to consider fn from -2 to 3 to are defined by the condition fn of x equal to sine of nx divided by n. So you see that here we have bounded function because it is continuous. They are continuous, they are bounded, continuous on a bounded set. So we know that it is dominated. Look, so let us just check it. Let us just take it. First of all, we must compute f of x, which is the limit of the pointwise limit of our function f of x, fn of x. This will give us 0 if x is 0, because if x is 0, this is always a constant sequence that is 0, and it will give us something that is also okay. This is always 0. So let me say erase this and write everything. I write the limit as n goes to plus infinity of 1 over n sine of nx. So you see that this function, this sequence is bounded, and this sequence goes to 0. So the limit is 0 because this is bounded and this goes to 0. So the product will give 0. So this is our f of x. This is our f of x. We've already written it. This is our f of x. So we expect the limit of our integral to be 0 because our f of x is 0. We only need to find a function that dominates our sequence. So secondly, we must then try to see if I compute fn of x, can I get that all this is less than some expression here that doesn't depend on this n? That is the question I'm going to solve now to see if it will be dominated by something. So I compute this, which will be the absolute value of sine of nx divided by n. So my aim is to see if this will be less or equal to an expression here of x only. So an expression of x only without n inside. And this expression I will call it g of x. And I will check if I can integrate g of x and find something that is finite. That is the strategy I'm going to use here. So let's continue and see if we're gonna achieve this aim. But the absolute value of this is the absolute value of sine of nx divided by n, because the absolute value of the quotient is the quotient of absolute value. Because n is positive, so the absolute value of n is just n. But then we know that the absolute value of sine is always less than 1. So all this will be less than 1 divided by n because we didn't change anything in n. So you see that this is an expression that doesn't, so it depends on n. We don't like it to depend on n, but let's just think a little bit. We have 1 over n, right? 1 over n is always less or equal to 1 because you see if n is 1, it is 1. If n is 2, is 1 over 2. If n is 3, so it stays always less or equal to 1. So this is our g of x, which is a constant. So let us check if g is integrable. If we integrate from -2 to 3 of g of x dx, we will get the integral from -2 to 3 of dx, which is 3 plus 2, which is 5, which is finite. So the integral of g is finite, and then we can use the Beppo-Levi theorem, which says that the limit of this integral, the Lebesgue dominated theorem, it says that the limit of this integral sine of nx divided by n d of x is just equal to the integral of 2 to 3 of the limit as n goes to plus infinity of sine of nx divided by n dx, but we computed this, we found that it was 0. So we have the integral of 0 d of x, which is 0.